We'll start in 1 minute. Today we'll continue in section 7.5, strategy for integration. And if there's time left over, we'll start section 7.6 on using integration tables. Well, let's review what section 7.5 has to say. There's a brief list of an integration strategy. It's given in the textbook. The first one, simplify the integrand if possible. Number 2, look for an obvious substitution. And 3, classify the integrand according to its form. And if that doesn't work, try again, try something else. So far this semester, we've reviewed the substitution rule from chapter 5, section 5, integration by parts in section 7.1, trigonometric integrals from section 7.2, trigonometric substitution from section 7.3, and partial fractions, chapter 7, section 4. Okay, we did the first one, and that leads us to this next indefinite integral. The indefinite integral of sine of x to the third divided by cosine of x. So what did you try, or have you tried this one yet?
I would split up sine theta and sine squared x from sine of x, and then change the sine squared of x to 1 minus x squared.
I couldn't hear what you were saying, so I'll guess. You converted sine of x to the third to sine of x squared times sine of x? Yeah, that's what I would do. So in the numerator, instead of sine of x to the third, write sine of x squared times sine of x over cosine of x. Well, a reason for doing this is we can replace sine of x squared with 1 minus cosine of x squared. So we'll have the quantity 1 minus cosine of x squared times sine of x all over cosine of x. I'll go ahead and write a little bit more detail than is absolutely necessary, but the next step, let's, in the numerator, distribute multiplication by sine of x. So the numerator becomes sine of x minus cosine of x squared times sine of x, all divided by cosine of x dx. And then we'll write this as a difference of two terms, sine of x divided by cosine of x. And for the other term, we can cancel one factor of cosine of x. So we're just left with minus cosine of x times sine of x. Sine of x divided by cosine of x is tangent of x. Or we could even integrate this, but let's go ahead and convert it to tangent of x. I'll write two separate integrals here. Okay, we know an antiderivative of tangent of x. That one is the natural log of the absolute value of secant of x. And then the other integral, the integral of cosine of x sine of x dx. We have a couple of options. We can use the substitution rule in one of two ways. So I'll rewrite the second integral down here. We'll look at it in isolation. The indefinite integral of cosine of x sine of x dx. Using the substitution rule, one option is to pick u to be sine of x, so that du is cosine of x dx. And then upon substitution, we get the indefinite integral of u du, which is u to the second divided by 2, or sine of x squared divided by 2. So that's one option. So we can write minus sine of x squared over 2 plus a constant. The second option, if using the substitution rule, you could assign u to be cosine of x, so that du is negative sine of x dx. That also works, but this is satisfactory. Okay, the next page. This one, the indefinite integral of x times tangent of x squared dx. So to me, this looks like I want to try a particular method. Is there a particular method that sort of stands out as one that we should try for this one? Does anybody on YouTube have a suggestion? Which method? So how many know but don't want to answer? Okay, the method I have in mind is integration by parts. The integrand is a product of a polynomial and a trigonometric function. So I'm going to try integration by parts. I'll assign u to be equal to x, so that du is equal to dx. And then dv is tangent of x squared dx. Well, it might not be immediately apparent what an antiderivative of tangent of x squared is. But if we replace tangent of x squared using one of the Pythagorean identities, so in other words, dv is equal to, let's see, what's tangent of x squared equal to? Yeah, secant of x squared minus 1. So we'll put that in parentheses, secant of x squared minus 1, and then multiply that quantity by dx. And now we can find an antiderivative of secant of x squared minus 1 with respect to x. An antiderivative of secant of x squared is tangent of x. And then an antiderivative of minus 1 with respect to x is minus x. So I'll remind you of the integration by parts formula, the indefinite integral of u times dv is equal to u times v minus the indefinite integral of v times du. Okay, so for our function, we have u times v is x times the quantity tangent of x minus x. And from that, we are going to subtract the indefinite integral of v times du. So v is the quantity tangent of x minus x, and then dx. We can go ahead and distribute multiplication by x on the left, x times tangent of x minus x to the second, and then minus an indefinite integral of tangent of x, so that's minus the natural log of the absolute value of secant of x. And then we're subtracting the negative of the antiderivative of x, so that means we're going to add x to the second over 2. And we can simplify a little bit more because we have like terms. So we might as well simplify it further. X times tangent of x minus 1/2 x squared minus the natural log of the secant of x plus c. All right, the next one, the indefinite integral of the square root of 1 plus x over 1 minus x. So you might remember a fairly common maneuver in college algebra for situations like this. So how do you want to start this one? So I'll give you a hint. We're going to multiply by 1. What form should 1 take? So 1 can take infinitely many forms. We just want one of those infinitely many. Hey, this is what I'll suggest. Multiply the integrand by 1 in the form the square root of 1 plus x divided by 1 plus x. So we're all in agreement that this is equal to 1. Divided x does not equal negative 1. Otherwise, if x is negative 1, then it's undefined. But okay, so we'll do the algebra. The square root of one thing multiplied by the square root of another is equal to the square root of the product. So in the numerator, we have 1 plus x times 1 plus x, which is 1 plus x quantity squared. In the denominator, 1 minus x times 1 plus x simplifies to 1 minus x squared. In the numerator, the square root of 1 plus x quantity squared is just 1 plus x. And then in the denominator, we have the square root of 1 minus x squared dx. So any ideas on how to evaluate this after transforming it a little bit? Yeah, notice in the denominator inside the square root, we have 1 minus x squared. So there's a trigonometric substitution for that. So the trigonometric substitution is x equals 1 times sine of theta. Dx is cosine of theta d theta. 1 minus x squared is 1 minus sine of theta squared. But 1 minus sine of theta squared is cosine of theta squared. So let's make those substitutions. So instead of 1 plus x, we'll write 1 plus sine of theta. And in the denominator, instead of the square root of 1 minus x squared, we have the square root of cosine of theta squared. And always remember the dx. Dx is cosine of theta d theta. And then we'll get something that's pretty easy to evaluate. we get, so for now we still have 1 plus sine of theta in the numerator. The square root of cosine of theta squared is cosine of theta times cosine of theta d theta. Cosine divided by cosine is 1. So that leaves us with indefinite integral of 1 plus sine of theta d theta. And we get theta minus cosine of theta plus a constant. And then we have to express this in terms of x. Based upon our substitution, or trig substitution. So since x equals sine of theta, theta is the inverse sine of x. So this is what we're going to replace theta with, inverse sine of x. And we also have to replace cosine of theta. So how do we do that? We use our assignment x equals sine of theta, and we can use right triangle trigonometry. So we'll label this angle theta. If the sine of theta is equal to x, then the side opposite has a length x, the adjacent side is 1. X over 1. And so the hypotenuse, I'm sorry, I messed that up. Sine is opposite over hypotenuse. So x over the hypotenuse is 1. Okay, so the adjacent side, using the Pythagorean theorem, will be the square root of 1 minus x squared. Okay, then the cosine of theta is adjacent over hypotenuse. So cosine of theta is the square root of 1 minus x squared. So our integral is inverse sine of x minus the square root of 1 minus x squared plus a constant. All right, the next page. So this time we have a definite integral. The integrand is the square root of x times e raised to the square root of x. This should be dx, not dy. And the lower limit is x equals 4, and the upper limit is x equals 9. Do you have a suggestion on how to start? How to find an antiderivative? Well, one of the suggestions in Chapter 7, Section 5 on strategy for integration, look for an obvious substitution. Well, maybe it's not obvious, but we have this square root of x. So oftentimes, in a case like that, we replace the square root of x with a single variable. Okay, I have the advantage of having worked this problem out. So I'm going to pick a variable w to be the square root of x. It'll be more convenient later if I pick w for this one. So if w is the square root of x, then dw is 1 over 2 times the square root of x dx. So we want to solve this for dx. So if we multiply both sides by 2 times the square root of x, we get 2 times the square root of x dw equals dx. But since I am assigning w to be the square root of x, this becomes 2 times w dw equals dx. So we will replace dx with 2w dw, and we'll replace each of those square roots of x with w. And we will also change the limits of integration. But let's make the substitutions first. Replace the square root of x here with w, and then e to the w, and dx is 2 times w dw. What should the lower limit of this transformed definite integral be? In the original definite integral, the limits are x values. And w is defined in terms of x. Specifically, w is the square root of x. So for the lower limit, when x is 4, what's the corresponding w value? 2. Square root of 4 is 2. So the lower limit of this is 2. And then for the upper limit, when x is 9, w is the square root of 9, or 3. So the upper limit is 3 for w. Okay, so we'll simplify the integrand a little bit. The definite integral from 2 to 3 of 2 times w to the second times e to the w dw. The only way I can think of evaluating this definite integral is to use integration by parts. So now I'm going to use u, integration by parts. I'm going to assign u to be 2 times w to the second, which means du is 4w dw. dv is e to the w dw. Whoops. And so w is e to the w. Okay, then the integration by parts formula, u times v is 2 times w to the second e to the w. Minus, let's see, let's just find the antiderivative, and then when we're finished, we'll evaluate it from w equals 2 to w equals 3. So this is u times v minus the integral of v times du, e to the w times 4w dw. So this is minus the integral of 4w e to the w. dw. Then let's isolate that integral 4w, the integral of 4w e to the w dw, and use integration by parts again. So this time pick u to be 4w, so du is 4 dw. Pick dv to be e to the w dw, so v is e to the w. Then when we evaluate this, u times v is 4w times e to the w minus the integral of v du. So this is going to be minus, I'll bring the constant 4 out front, minus 4 times the integral of e to the w dw. And we can go ahead and evaluate that because the integral of e to the w is just e to the w. So this gives us 4w e to the w minus 4 times e to the w. So this is what we get. We're going to subtract this entire quantity. And we'll get 2w to the second e to the w minus this quantity, minus 4w e to the w, and minus minus is plus 4 times e to the w. And we can evaluate this from w equals 2 to w equals 3. So I'll just take it one more step. For the upper limit, w equals 3. 2 times 3 squared is 18. So 18 times e to the third, because w is 3. And then minus 4 times 3 times e to the third is minus 12 times e to the third. And then finally plus 4 times e to the third. And then we subtract that quantity at the lower limit when w is 2. 2 times 2 squared is 8, so 8 times e to the second. And minus 4 times 2 times e to the second is minus 8 times e to the second again. And then plus 4 times e to the second. There's a little more simplifying that can be done, but this is okay for now. Okay, let's look at the next indefinite integral. So for this one, the indefinite integral of x to the third over the cubed root of x squared plus 1. So what do you want to do on this one? Well, maybe it's not obvious, but I'm going to substitute u equals the cubed root of x squared plus 1. So this is the same as the quantity x squared plus 1 to the 1/3. And then du is 1/3 times the quantity x squared plus 1 to the negative 2/3 times 2x, using the chain rule, and then dx. Well, we want to solve for dx. So we can multiply both sides by 3, divide both sides by 2x. And we can multiply both sides by x squared plus 1 to the positive 2/3. That's equivalent to dividing both sides by x to the second plus 1 to the negative 2/3. So dx is going to be 3 times x squared plus 1 to the positive 2/3 divided by 2x du. Well, since I'm defining u to be x squared plus 1 to the 1/3, notice that x squared plus 1 to the 2/3 is u to the second. You see that? So let's go ahead and make that change here. Dx is 3 times u to the second du over 2x. We have to deal with this x at some point, but for now we'll leave the x here. So what we're going to do, we're going to replace the x to the third in this numerator with x times x to the second. So we need to find an expression for x to the second in terms of u. So we can do that here. If u is equal to the quantity x squared plus 1 to the 1/3, that means if we raise both sides to the third power, u to the third equals x squared plus 1. And so u to the third minus 1 is equal to x squared. Okay, so in the original indefinite integral, I'm going to rewrite x to the third as x times x to the second. And eventually, we're going to replace x to the second with u to the third minus 1. We can go ahead and replace the cubed root of x squared plus 1 with u, since that's our assignment. And then replace dx with 3u to the second du over 2x. So in the denominator, I'll get a factor of 2x, and in the numerator, 3u to the second du. Okay, so this is how we get rid of the extra x. X in the numerator divided by x in the denominator cancels. One of the u factors from the numerator will cancel with this factor of u in the denominator. And then we also replace x squared with u to the third minus 1. Okay, so we'll do all of those things here in this next step. Replace u to x to the second with u to the third minus 1. And then 3u to the second divided by u is 3u in the numerator. And we're still dividing by 2 and then du. Okay, we get an indefinite integral that is pretty easy to evaluate. So bring the factor 3/2 out front. Distribute multiplication by u through u to the third minus 1. So we get the quantity u to the fourth minus u du. And then 3/2 times the quantity u to the fifth divided by 5 minus u to the second divided by 2. And then remember what u is. So u is x to the second plus 1 quantity to the 1/3. So we'll just write this 3/2 times 1/5 is 3/10. And then the quantity x squared plus 1 to the 5/3. And then minus 3/2 times 1/2 is minus 3/4. And then the quantity x squared plus 1 to the 2/3. So this is our final result on that one. Okay, on the next page, what are we going to do for this indefinite integral? The indefinite integral of 2x minus 3 divided by x to the third plus 3x. Yeah, partial fractions, is that what you said? Yeah. We can factor the denominator. So we get a factor of x and an irreducible quadratic factor, x squared plus 3. And so let's find the partial fractions. The factor x is linear, so one of the terms is a over x. The other factor is an irreducible quadratic factor, so the numerator will write bx plus c over x squared plus 3. So 2x minus 3 over x times x squared plus 3. We'll simplify this right-hand side with a common denominator of x times the quantity x squared plus 3. So we multiply a times x squared plus 3 plus bx plus c times x over the common denominator. So in the numerator, we have ax squared plus 3a plus bx squared plus cx. Okay, so now let's just focus on the numerators. The numerator 2x minus 3 is equal to this numerator, ax squared plus 3a plus bx squared plus cx. So we set 2x minus 3. We'll combine like terms. Ax squared plus bx squared is a plus b, this quantity times x squared. There's only one x term, so plus c times x, and only one constant, plus 3 times a. Okay, so the coefficient of x on the left-hand side is 2. So that means c is equal to 2. the constant -3 is equal to 3 times a. So if 3a equals -3, then a is -1. A plus b has to add up to 0 because on the left-hand side in the numerator, there is no x to the second term. So if a plus b is 0, that means that b is equal to +1. So our indefinite integral, instead of a over x, we can write -1 over x. And then bx plus c, since b is 1 and c is 2, we can write x plus 2 over x squared plus 3. Okay, so now we're in more familiar territory. So rewrite this. I'm going to write this sum of 3 separate integrals. So -1 over x dx plus x over x squared plus 3. And then the other one, the indefinite integral of x squared plus 3 dx. So this one is the indefinite integral of -1 over x dx is negative natural log of the absolute value of x. For the middle integral, we can use the substitution rule. If u is x squared plus 3, then du is 2x. So if we multiply by 1/2 times 2, I'll go ahead and write it. So we want the numerator to be 2x, but we have to compensate by multiplying by 1/2. So we get an indefinite integral that has the form, this has the form du over u. So the integral will be the natural log of x squared plus 3. And then what about the other one? Indefinite integral of 2 over x squared plus 3. Well, it's going to involve inverse tangent. So why don't we do this one by using a trig substitution. You can memorize the formula, but it might be worth the effort to practice a trig substitution. So if we replace x with the square root of 3 times tangent of theta, that's the square root of 3, then dx is the square root of 3 times secant of theta squared d theta. I'm going to, instead of trying to squeeze it all there, I'll get another piece of paper. Okay, so let's take a look at this. Okay, so x squared plus 3. Well, since x is the square root of 3 times tangent of theta, x squared is 3 times tangent of theta squared and then plus 3. And this is 3 times secant of theta squared. So we make substitutions. So dx can be put in the numerator, so I'll just write 2 times what dx is equal to, 2 times the square root of 3 times secant of theta squared d theta divided by 3 times secant of theta squared. Secant of theta squared divided by secant of theta squared is 1. Bring the constant 2 times the square root of 3 over 3 out front. And so we get 2 times the square root of 3 over 3 times the indefinite integral of d theta. So this is 2 times the square root of 3 over 3 times theta. And what's theta? We have to replace theta with an expression in terms of x. So that is determined by our substitution. So divide both sides by the square root of 3. X divided by the square root of 3 is tangent of theta. And so theta is the angle whose tangent is x divided by the square root of 3. So our answer to this part, 2 times the square root of 3 over 3 times inverse tangent of x divided by the square root of 3. It looks like we're about out of time. So online, go ahead and sign in for attendance. Oh, Joshua. Sarah? Oh, that's it. Thank you.